Welcome back. We're going to continue our discussion on the idea of molecule polarity. Now, what we're going to learn is a good foolproof method, while there are exceptions to that. But again, considering the amount of time we have in the course, getting into every single exception is not possible. Okay, so the method is very much gives you a broader outlook into understanding molecule polarity. Now, previously we had learned whether a bond is polar covalent or non-polar covalent. But that was about the bond. But what about the molecule itself as a whole? Well, we didn't learn it. That's exactly what we're going to get into. This is a starting point, okay? And the concept we're going to learn it is called a valence shell electron pair repulsion theory, also known as VSEPR. Let me repeat, it's a valence shell electron pair repulsion theory and Lewis structure. They kind of feed into each other. Now, this is the textbook definition of valence shell electron pair repulsion theory, and I'm not going to quiz you or test you what the definition itself on an exam. There you go. But what does this long, lengthy definition say is every molecule has some kind of a central atom, okay? And the electron arrangement around the central atom can significantly influence the molecule's polarity. That's kind of what VSEPR theory is referring to. Now, what type of geometry that VSEPR theory contributes to is molecular geometry. Remember that? Lewis structures, well, in a nutshell, Lewis structure primarily deals with electron arrangement between atoms. Simple as that. And what type of geometry does a Lewis structure contribute to? It's electron geometry. Now, for people in the online environment, I can tell you, you do not have to memorize the table because the table will be available to you, whether you're use it for a quiz or homework or an exam. For people in the online, in the in-seat environment, we have to come up with some compromises on how, and then I'll probably walk you through in the in-seat environment how to actually remember the table. All right. But what is one thing I need to know to be successful with this concept? And something I need to recall from my knowledge repository is valence electrons, Roman numerals. So I'm going to make two separate videos and probably throw in a practice in one of the videos to explain the concepts and how to use the table. It's very, very simple. There's nothing complicated, nothing tedious. And again, the Roman numeral is something it's already in the periodic table. So you're not memorizing anything really to understand this concept. It's very simple. So here's the periodic table, and I have highlighted the boxes of what the Roman numeral I was referring to, even when we learned it earlier. 1A means one valence electron. So for instance, lithium has one valence electron, right? We've learned it before. Phosphorus, for bonding purposes, we are going to consider the Roman numeral as it is. So it's 5 valence electrons because it is 5A, right? And this is 1A, right? So you have to remember the Roman numeral from the periodic table. That's what you're going to use to solve these problems. Again, you're not memorizing it. You just have to remember, hey, this is what I need to use to solve the problem. All right. So I'm going to stop the video here. This is primarily introducing the idea of valence shell electron pair repulsion theory and Lewis structures. In the next two videos, I'm going to walk you through how to construct structures and then use the table to develop a decrypted code, which then you would use to identify the geometry of the molecule, whether molecular or electron, and then based off of the molecular geometry, you can identify whether a molecule is polar or non-polar. All right, so stay tuned.